Okay, yeah. So at this site, I've got the latest PDF version of the slides at this site now.
Excellent.
So one could, yeah, if somebody photographed their screen, they'd have this access to the slides that way.
Right, I'd like to welcome those who've joined us, particularly Tom Gilb, who's going to be our presenter for tonight, and all 12 of you who've joined us online. I hope there'll be a few more along in a minute because we have got a few more people registered. For those of you who've not been to one of these conferences before, let me tell you the emergency exits are behind you and that we're not expecting a fire alarm tonight. So next month, I'm very fortunate that we've already got a talk organized at the beginning of May. It's going to be the first Wednesday in May, which I think is the 4th or the 5th of May. And that's going to be Nick Tune talking about socio-technical aspects of teamwork. More details, if you like, on the BCS SPA.org website. And you'll also be getting a notification about it in a few days. Okay, I think that's enough of me chatting. Let me hand the camera over to Tom, and he will take us through tonight's talk.
Okay, can
Tom.
anybody see me?
No, I think you have to share your webcam now.
Okay.
There we go.
So you can see me now?
Indeed.
Okay, I don't have a picture of me, but I'm okay. That's fine. So I start the talk.
Please do.
Okay, fine. So this talk is scheduled to take about an hour and a half. I've got my timer on the watch, and we'll try to stop at that point and perhaps take questions or discussion. Is that correct, Imo?
Microphone is muted. We aim to finish around about 8 p.m. our time,
right,
which is an hour and a half, give or take 10 minutes or so of questions.
Okay. Okay, welcome everybody. My subject is complexity in software engineering or IT area. I use this word I've invented called technoscopes. They're sort of like microscopes or telescopes. They help us see the little viruses in the complex system. And I'm offering everybody here a free copy of my booklet, Technoscopes, which has about 100 different practical tools for dealing with the complexities of IT systems. So you'll find the links to that on the left-hand side. If you photograph the screen, you'll get the link to the slides, which is this set of slides is at that link there. And here's the book, which is free to the listeners, but we're otherwise selling it. So if you give a reference to it, that's the proper link. See, some academics many years ago started looking at a thing called wicked problems, which at least became an academic favorite. And of course, we have a wicked problem we're all facing right now, the planning to get rid of the coronavirus or harness it in some way. And they made 10 statements about wicked problems, which are about complex systems. Although when I started, they all sound like good common sense and sounds fine and useful. But when I started analyzing them in relation to the tools I have, I found that if people use the tools I'm going to present, then in fact, most of these statements are actually not true. The detail of that is in slides at the end of this talk, which I'm not going to present, but they're at the end of the slides if you want the detail of my arguments why these wicked problems are not necessarily wicked if you have proper set of tools. Here's Jeff, who looks at another class of problems. They're not so wicked. He calls them tame problems. For example, stopping people smoking, I think, matches most of these points. And but our interest is when we don't have a tame problem, we have something as wicked as the coronavirus problem, or as we all know, software is one of the most complex things on the planet. Here are some nice little pictures to remind us about what complex systems have as characteristics. For example, there are very many different views of the problem. There may be some ideological constraints, like don't kill off your grandparents. Many possible intervention points, like quarantine or financial aid to motivate people to stay in quarantine. Political constraints, politicians trying to make points that they're helping and we should vote for them next time, perhaps. Economic constraints. Norway has saved a lot of money from oil and so doesn't view itself as having an economic problem, but many other nations do. Great resistance to change. It isn't easy to sit in with your family for a few months in the house. And here's more and more and more. But I think we can all recognize that these ideas of wicked or complex problems fit very nicely with the COVID-19 pandemic. Here's a third view. We're going to take a look at stakeholders in a moment. And one problem with stakeholders is they all have a different view and a different motivation. They don't all agree on what to do. And this causes problems of choices, strategies, and things like that. Okay, so wicked problems. And something like building a government IT system for, say, the National Health Service is a good example of a wicked problem, the kind of thing we haven't seemed to have solved very well. Now, I have a set of ideas, my 100 tricks in the Technoscopes book, which are based on a planning language I developed called Planguage. And I'm giving you later in the slides a free digital copy of the book which defines Planguage for those who want to go into more depth. But I'm going to focus on 5 different areas of my solutions, 1, 2, 3, 4, 5, and the whole talk is divided into these 5 parts. Here I picked out a couple samples of the Technoscopes book so you get a feeling for the 100 different things. Here's a number 31 where I talk about how to tackle risks, assumptions, and issues in general, and give specific examples on the left-hand side of how you do it in the planning language. And here's another sample. Again, here's the basic idea on the right-hand side, and on the left-hand side are practical examples of doing it. So if you really want to go deep after having heard this talk, I'd suggest you grab yourself a copy of the Technoscopes book and study it 1 Technoscope tool per day for the next 100 days, and then maybe we'll all be out of quarantine by that time. So number 1 of the 5 is by using something we can simplify and call it black box analysis. Here's a picture we'll later enlarge of the black box, and a lot of people trying to peek into the black box and understand artificial intelligence systems. But in our practical terms, I have 2 ways of looking in the black box. One is called stakeholders. This is very much more detailed and rigorous than just looking at users and customers, which is about as far as the IT business has gone, 95% of it. But more and more people are beginning to realize if they're really going to solve large, complex, wicked problems, they've got to take a look at maybe 50 stakeholders, to take an example, rather than a user and a customer, which is the oversimplification that current agile methods give us, with user stories, use cases and focusing on the customer. All very nice. It's just that you're missing about 49 critical stakeholders. And by definition, a critical stakeholder is one that can kill your project if they don't like what you deliver. Now, what stakeholders are interested in is a set of things we call values. You could call them requirements or objectives or qualities, but they are the multiple dimensions of goodness that we have to deliver to keep the stakeholders happy. You notice we're even in this attempt to simplify and look outside the black box, we have kind of complexity here. We have first the complexity of a very high volume of stakeholders, and real systems may have 200 of these, not just about 20, which is here. And we have 10 different variables, not just, for example, the functionality of the system, but all these values. And notice that one stakeholder can have multiple values, and one value can have multiple stakeholders. So right there and then, we have this kind of complexity, even at the level of trying to simplify and get an overview. In this case, we have a digital tool called valplan.net, by the way, which helps us keep track of these things. And we can see things like, here's a value, but we don't know of any stakeholders who care about equipment capacity. And here is a stakeholder like a cultural event, which doesn't have any values. And by definition, stakeholders are there because they have critical values that we have to listen to. So we can at least analyze and say, we've got to do something about the fact that we don't seem to understand which values they care about. It could be one or more of these, and it could be things that are not on the list. Anyway, stakeholders and values is a way of looking at a very complex system. Think national health system, IT system, or any other large government system would be fine. And trying to understand it from the perspective of what do the stakeholders think, what do they need, or exactly what are the set of needs we have to deliver for the whole set of stakeholders. Here's the black box, and here these are little individuals that are trying to understand an artificial intelligence system by peering into the black box with various tools. And part of what we're going to do in this talk is take a look at some of the tools that allow us to understand what's going on inside the black box, not in technical detail like each line of code and each piece of data, but what the major values it produces and the major costs it has is. So this is our symbol for people and stakeholders trying to understand what's inside this extremely complex system. Here's a slightly enlarged view of what we just looked at, slightly more readable. We in the 5th and 6th of March, we had a class of the same kind we're planning to do at BCS and have done before, where we picked a topic, and the topic was the coronavirus planning for Norway. And so we had 4 teams that generated this list of stakeholders and this list of values or objectives. And all of these values or objectives were defined and quantified and used to select strategies and understand costs. We'll show you some more information about that shortly. Okay, but again, here's one way of looking outside the black box, understanding it. Who are the stakeholders? What do they want? And here's another way. The values. Another way of thinking about the values. The values are the main point of any project, to deliver a set of values at satisfactory levels, so the stakeholders get off your back. Now, a stakeholder is not so simple. In fact, a stakeholder has many types of values, and different stakeholders have different, for example, risk aversion or innovation interest or legal and environmental points. And so one way of looking inside the black box of who is the stakeholder is to have a list of typical stakeholder, you could call them values at this point, or characteristics or attributes, and then try to understand more or less exactly what is the typical stakeholder, say a university, what are their legal constraints and legal necessities to that we have to satisfy in order to allow them to be the stakeholder they are. For example, be a valid university. So again, this is complex in a way compared to just looking at a stakeholder and saying, what functions do you want? Suddenly you have 10 variable dimensions. And just because a stakeholder says doctor doesn't mean all doctors have exactly the same set of these. Different doctors of different types will in fact have a variable range of considerations they have to look at. The point is, by understanding the stakeholder and understanding their values and setting up the values we have to deliver in the system, we've set the stage so that we can select architecture and design and get the best, meaning most cost-effective designs in there first and early. We'll talk more about this prioritization and decomposition of the architecture as we go along in the talk. Anyway, here's a way of modeling the stakeholder through a set of typical characteristics that we need to ask questions about, analyze, get some data about, and decide that we're going to deal with it or not. Here's a very, very basic tool. And in fact, if there's just one thing you picked up of very practical tool from this whole lecture, it would be what I call an impact estimation table, which I've invented and used for decades. Here's a basic overview of what an impact estimation table does. It looks at various solutions, and a synonym for solution is design or architecture or strategy, the means by which we're going to reach certain objective. And we might need several solutions, or we might have alternative solutions, doesn't matter, but we're basically going to pull in some solutions. Maybe your IT architect you can view as somebody doing this initially. And the point of pulling in solutions is that you have solutions that will in fact achieve the right levels of your objectives on time at costs you can afford. So what we're going to do is for every solution, we're going to say, what is the impact of that solution on my objective? You know, will this solution reach my objective all alone? Then I don't need the other ones. Or will this solution and this solution probably reach my objective? Then I don't need this one, but I do need these two. So we go further than just saying the impact is high, low, or medium, or 1 or 2 or 3 stars. That, for example, quality function deployment or balanced scorecard would do. We're going to actually estimate numerically the impact, and we're even going to give evidence for why we've made a certain estimate, and we're going to give the source of that evidence so it can be quality controlled. I won't talk too much more about that, but it's in the books, for example, already mentioned. Now, once we found solutions that have enough impact on our objective, we have to ask another question is, what do they cost? And that's in terms of time to deadline, money, skilled staff. Look at the staffing problems we have for the medical personnel in the coronavirus. That's a non-trivial thing when half of them are all gone because they're quarantined. And so a solution not only has to reach our objectives, but it also has to be within budget, within deadline, and within the skilled personnel. So we need to estimate numerically for each solution that we're thinking of doing, what will it cost, and ask a very simple question: can we afford it? Can we wait for it? Do we have the personnel? And if not, maybe we can't use that solution, even though it would solve our problem. It's too expensive. It will come too late. Things like that. Look at all the timing problems with the coronavirus. You know, there's this big deadline when we have a vaccine in about 18 months or something like that. And there are shorter deadlines like flattening the curve kind of deadlines that we're all subject to every day. There's another part of the structure of an impact estimation table where we can try to sum up the impact of any set of solutions and say, is the sum probably enough to get us to our objective, or maybe beyond our objective, or is it so weak that there's no way these 3 things are going to get us to our objective? And by the way, if we add up all the budgetary figures, you know, will we exceed the deadline the budget, etc. Then there's another thing we can do. Once we have the idea of how much impact we have and how much cost it will be, we can look at a benefit to cost ratio, or think of this as profitability or cost effectiveness. And obviously, if we're not going to implement everything at once, which would be big bang waterfall, you know what to think about that. We're going to do these perhaps incrementally in sprints. Then we should probably pick the solutions that have the best benefit to cost ratio. Do you think that sounds like a good idea, as opposed to the worst benefit to cost ratio? Would be probably a bad idea of starting. You might risk using up your entire budget and only achieve 5% of what you wanted to do if you chose the prioritization strategy of early sprints are done with the least cost effectiveness. Now, here's a slightly, that was the structure, but here is the more realistic picture. So this is the impact estimation table used in the classroom exercise of fighting the coronavirus in Norway on the 5th and 6th of March. And here are 4 different teams. And what I've asked each team to do just for the exercise is pick a value, collect information, education, get people where they need to be, healthy employees, and stay healthy, and then to quantify each one of these. And so a scale of measure invisible here, but it's been defined. And then to establish 2 points where we are now, the status, that's the number, how good or bad we are at this moment in time, say 6th of March. And then a wish level is how good we want to be when we are successful. Okay, so we're actually defining success with these numbers here. Now, the impact estimation table then brings in these bright ideas. You see the light bulb symbol, and these are solutions or means or architecture, just the name or the name tag of them. These could be defined in a page or 2 elsewhere, but right now we just have their high-level name. Same thing here. This is just a tag or high-level name of what could be a whole page, which we'll show you later, of detail. And so the question is, health architecture, how good is it for reaching our goal of collect information? Now, without going into the detail, of which there is plenty, but not here, we've estimated that it will bring us 13% of the way, or 5 points here on up to 55. That's that number there, which isn't very much, but it's better than nothing. The transport architecture solution is evaluated to get us halfway to this goal, halfway from 50 to 90, which is jolly good, but not good enough. Tour's architecture, Tor is the lead of the team there, by the way, name of a Norwegian man. They've evaluated that their architecture will get us 63% of the way, which is very good. And the workplace architecture done by another team is evaluated getting us 75% of the way. Now, none of these solutions gets us all the way to the goal. So we either have to find completely new solutions that do get us to 100% of the goal, or somehow hope and combine. For example, if I started with this one, which hopefully gets us to about 75% of the goal, then I could add maybe, not this one, it's probably not going to get us there, but I could add one of these in later sprints and hope the combination of that plus that gets me to 100% of my goal. Now, that is to be seen. Right now, we're just theoretically estimating and trying to understand our options. Unfortunately, any strategy you have has a thing which engineers call side effects. That is, they're not the main reason we brought them in, but they're going to happen whether we like it or not. So if this were the main effect, workplace architecture on collect information, then all these other things are side effects. That is, they're not primarily intended, but they're there whether we like it or not, for good or bad. And if they're positive, that's fine, but they can be negative. They can also be unknown. That is, we haven't got the data to evaluate what happens. There are lots of unknowns in the coronavirus thing, like how long the virus lasts on plastic and things like that, or whether how long immunity lasts. We've got lots and lots of known unknowns. But however, it's very good engineering practice, and I have to admit, I'm trying to teach you systems engineering, so you can do software engineering, and looking at side effects is a part of any serious engineering discipline, so you don't get surprised by the side effects in bad ways. And like a good chess player, you can take into account good side effects and say anything that has a lot of good effects in total, and here is a total number for that called the sum of values, is probably a pretty good thing to do. For example, this is a loser at 30. You add up all the effects we know about here, it's only 36%. The other three are pretty strong and roughly the same. So we could choose almost any one of these. This happens to be numerically the largest, but not by much, so it doesn't much matter. Now here, for each one of these architectures, we've tried to look at the number of days to implement within the framework of our deadline and the capital cost. And we can also add up the percentages there. This is the sum of the development resources, okay? And we can use that to compute the value to cost ratio. That's this number, sum of values, over this number, sum of development resources, 12. And a very high number pops up here, and the app puts it in green because it's the best one, 40 points, if you like, value to cost ratio, cost effectiveness. But this is very close, isn't it? 39.20, so it probably wouldn't make any difference from a cost effectiveness point of view if I used this one or this one first. However, this is nowhere near, and this is even further away. So they're not good candidates to start with, but they could turn out to be better than we think they are. Another thing we've done here is we've made it invisible here to keep things simple, but we actually look at the plus minus range of the estimate. We look at the credibility of the evidence, and to make a long story short, if we say, if the worst case kicked in, if Murphy's Law, if anything can happen, it will, kicks in, what would be our best option? And it turns out this one here, 25.80, is when things go badly and things go wrong, is actually a slightly better alternative than transport architecture. So a skeptical or conservative manager might say, let's do this one first. The second line here is actually looking at the credibility. So this one wins in credibility. But it turns out if we look at the plus minus uncertainty and the credibility, strangely enough, this one here wins. Now, here's an even simplified view of exactly the same thing. Any spreadsheet like that can be easily turned into a bar chart like this. So here are the four different alternatives. Here is the sum of the values. Here's the sum of the costs, and you can see, aha, these all have pretty much the same value and quite a lot of value, and it's almost a toss-up what you do here, because these are not, these estimations cannot be exact for various reasons. So you could choose any one and just go with it and see what happens. But this is a way of presenting to management their options and saying, well, pick any one you like because it doesn't make any difference, but this doesn't seem like a good idea because you're not going to get very much value for, even though it's a little bit cheaper. Okay, so this is a way of understanding, even this is a way of looking at the complexity of all of these requirements and all of these values and all of these solutions and all of the different ways of estimating and getting evidence and plus minus uncertainty, and the ratios. This is actually a simplified view of maybe a national health system, or in this case, in fact, coronavirus planning. But we can simplify this simplified view even more when maybe presenting it to a government minister and say, these are your options. So these are tools for simplifying the incredible complexity that's probably in that real black box, like the whole national effort or international effort for fighting the coronavirus. Okay, tool number 5, sorry, number 2 of 5 is the idea of dealing with the designs and costs incrementally. In other words, we don't design everything at once, the big architecture, and make the one big estimate. Let's call that Big Bang waterfall. But a way of dealing with the complexity of a system is to deal with it incrementally. Now, here's a symbolic picture. Here are 2 values, usability and speed. Here is the goal level, the success level. Anything beyond this is success. Here's what we call a tolerable level, and anything below that is intolerable or failure. And here's where we are now in the past. So as we deliver value increments, you might call them sprints, although sprints in Agile today are more or less delivering code and not really explicitly delivering any numeric value or measuring it. So here we're explicitly focusing on delivering value, even though we might not write code to do it. Sorry. As we implement, we measure how long we've gotten, and at this point, with we've passed the tolerable level into sort of a have a tolerable system, but not yet a successful system. And as we do increment number 8, we've reached success. On increment 7, we reach success with speed. Now, while we're doing these increments of trying to deliver value, we're also consuming resources. So each cycle consumes part of the budget. Here's an intolerably high use of money. And we're still in the tolerable level. We've exceeded the budget ever so slightly, but probably be forgiven for that when we've reached success, and we're not yet intolerable. So this is a graphical model of 2 value dimensions. In reality, we might have 10 or 100 value dimensions we are tracking simultaneously, and that makes it fairly complex, but we're still looking outside of the black box where there could be 59 billion combinations of logic times all billion combinations of data hiding inside the black box. So this is complex, but it's a lot simpler than actually trying to read the code and understand what it's doing for usability, or what it's doing for speed, or what it will cost. Okay, so but in the real world, we're typically at any one level of concern, like top level of a project, tracking usually what I call the top 10 critical values, only 2 here, and from 2 to 5 resources, long-term, short-term resources. Example of long-term resources could be the technical debt or the maintenance costs of the system. Now, I want to give you a practical example of doing this with a vengeance. Let me introduce to you Harlan Mills, who I cooperated with quite extensively in the old days. I consider him to be the Leonardo da Vinci of software engineering. Here's a link to about 500 of his papers if you want to read the Leonardo da Vinci papers of software engineering. He also is definitely an agile pioneer, as we'll see, and he invented something called the Cleanroom method. You can find books and papers on that by Googling it. It's a very advanced software development process that most people never heard of, do not understand. However, as we shall see, I would claim it is a perfect project management system for complex projects. And that's based on the experiential data we're going to share with you. Here's a link to the original writings on it from 1980, and that's after 10 years of experience of trying to crack the problem of, which still interests a lot of people today, when you win the lowest bid fixed price for a large, complex system, how do you make sure you don't exceed that cost and you make money? And how do you make sure you deliver it on time? Harlan and IBM Federal Systems Division cracked that problem, which most people don't seem to have cracked today. everybody runs over time, everybody runs over budget, and they don't even deliver what people wanted. The failure rate of waterfall projects was very roughly, look at Google it, 50%, and Scrum and Agile are not much better in terms of failure rate. Here we have, let's call it a 0% failure rate. Now, unfortunately, since this fantastic method was never sold or spread by IBM, they just used it internally, and even only in one part of IBM, the place doing space and military software, the Federal Systems Division, it isn't that well known. But as Santayana said, those who do not remember the past are condemned to repeat it. In other words, we are going to keep on failing to deal with our complex systems and master them until we learn methods that have in fact been used in the past to master them, like this. Here's a quotation from Harlem, which I quite like. It's related to everything in this talk. If you want qualities, and another word for qualities is the values that stakeholders want, you must design them into the system. You don't test them into a system. It's amazing. We actually have a rampant IT culture that talks about testing as a form of quality assurance. And it seems to think that if we test enough and long enough, we'll get rid of all the bugs, and therefore we'll have all the quality we need, which of course doesn't deal with security, technical debt, or anything else, just the bugs. And it's a very bad way of doing it. So we've got to change our culture. So we say that the multiple qualities we need will be designed in by an engineering process. You might notice that process is totally absent from most IT architectural methods and most agile methods. It just ain't there. But we're going to continue failing until we learn what engineers have long since known. And you can see in any well-engineered product that the qualities or values have to be consciously designed in. We're going to take a look at the design process used by IBM Federal Systems Division. Testing to get quality is not only impossibly complex, because but it will also take infinite time, and that won't be very helpful in getting the qualities you want on time. So here's a one-page summary of the experience, and I'm going to quote parts of it. But he's doing some military projects and some space projects. And let's take one quotation. He talks about doing things in 45 incremental deliveries on the LAMPS project, 200 person years of effort. Now, clearly, with today's eyes, we'd call that agile methods. It's using what I call 2% steps. They're actually monthly steps in a 4-year project. But clearly, it's agile, and we're going to see more of the agile parts of it. Now, here's the bottom line at the very bottom. There were few late or overrun deliveries, that means cost overrun, in that decade, 1970 to 1980, and none at all, in other words, perfect project management. Every extremely high quality or extremely complex military and space projects, absolutely state-of-the-art, without running over the deadline or budget. No projects at all of the real projects done at IBM Federal Systems Division in the past 4 years. In other words, they've totally mastered complex systems. And I believe this is a recipe anybody can use. Let's call it advanced agile. We'll look at it in more detail for getting perfect control of complex systems, just like Harlan and his team did many decades ago. Now, Harlan introduces the following idea, which we're going to look at in more depth: design to cost. Now, this is an engineering idea that if you give a smart engineer a challenge, make this go faster, make it cost less, they can technically design it so it does. And so Harlan's using design to cost. I call it dynamic design to cost because it's done not once at the beginning, but it's done at every iteration or every sprint. And he talks about a continuous process, in other words, the agile process, and relentless rectification, in other words, constantly being agile, changing and improving things as the data says you have to. So let me introduce you to a colleague of Harlan, Robert Quinnen. He was the architect in Cleanroom, and he describes his role here, again, on one page, which I published in 1988 in the Principles of Software Engineering Management book, which is well before any Agile manifesto, you'll notice. But this is some of the best Agile stuff the world has ever seen. And we'll look at this in more detail. For example, Quinnen talks about developing a design, okay, estimating its cost. That's what I showed you on the impact estimation table earlier. And then ensuring that the design is cost effective. In other words, does it give the impact we need in relation to what it costs? Again, the impact estimation table can be used to keep track of that. Here's a little flow chart he uses, which might be interesting, not least for its detail. If you like, this is about cost estimating to give a formal bid on a contract for a sub-supplier. And begin to look at the detail, it gets quite interesting what disciplines and processes they go through to get there, to make sure it's initially cost effective on the surface of it. And that's approximately what the impact estimation table does in the first instance. Okay, here's another diagram making sure that the design is cost effective. So we start off with the what we just looked at, cost proposal, get a contract, and then during the project we get some data sprint by sprint. We measure, and we can use the impact estimation table to track and measure, and then we put the data in our project database, which later gets accumulated into a historical database. I visited this group many times, and I captured with me a 20-page document made by their colleagues Walston and Felix, which captured dozens and dozens of parameters about each project, like were they using the inspection method, were they using this and that structured programming method, and so they can begin to understand from their historical data what things will probably cost. And that's something I think a lot of us are totally missing the idea, but it's certainly part of what we've seen a lot of in the COVID-19 thing, this desperate thing. We have no data on COVID-19. It's new. We must collect it as fast as possible. And only by collecting data from different countries can we begin to understand what we need to do in our country and what will probably work. So that's a very interesting element. They were very more advanced than anything I've seen before or since. But so long story short, they're doing cost performance monitoring and trying to make sure that they're not suddenly using too much money and time compared to what they're planning to do. Quinnen then uses this phrase, an iteration process. So in Agile, we do talk about iterative delivery, trying to meet cost targets by either redesign or by sacrificing planned capability. In other words, when he gets into a problem where it's the design they just put in this sprint is costing 3 times as much, or is time or budget, then we have to stop and say that design, even though it may be effective in delivering our values, is stealing too much of the budget, and we can't do it. Therefore, we have to find a better design. Best redesign. If we can't find a better design, then we have to sacrifice some planned capability, like, for example, future technical debt costs or something like that. This is a very interesting view of dynamic architecture or dynamic design. We'll take a look at that process chart on the next slide. But in the meantime, he makes this statement: design is an iterative process. And this is quite fascinating. In other words, design is integrated at each sprint. Is another way of thinking about it for Agile people. And of course, design itself is absent from most people's sprints and scrums and things like that. So we need to plug design back into Agile. And we're doing upfront design, which is what IBM did, but then we're modifying the design when the upfront design is measured sprint by sprint and shown to be costing too much, for example, or not effective enough. And so here is the chart of what I call dynamic design to cost. I also like to use the term, this is agile as it should be. And I've written a whole book on that called Value Agile, which is one of the courses we were planning to hold this week at BCS. But here anyway is a free copy of the Value Agile book, where I go into detail about agile as it should be. But it's pretty much the same as is here, and basically we're looking at here's the design process, but here is the change of the design. Change of the design, or the change of other requirements or contractual obligations to some degree in order to meet primary cost commitments and primary value deliveries. So you can study that at your leisure, but I think it's a beautiful example of how Agile should be, with design integrated into the loop and cost integrated into the loop. So this is design as an iterative process. So Quinin again, they iterate through a series of increments, thus reducing the complexity of the task. So the point he's making is that a complexity reduction method is that we do 1-2% step at a time. We don't do 50 times 2% or 100% of all the steps at once. That's called Big Bang waterfall. So every agile person knows that this is what agile is primarily about, is doing things in small steps so we don't get overwhelmed and we can deliver things early. Although most agile practices are missing the idea of measurement and built-in design, and I'm suggesting we need to plug that into the agile frameworks that we have if we want control over complex systems. If you have a very simple system, just keep on programming. Don't worry about what I'm saying. I have no message to you if you have really simple systems and can just get what you want by programming. Another thing that happens through a series of increments is you're increasing the probability of learning from experience. You know, we can estimate all we want with new technology and complex systems, but we're going to be wrong by and large. Hopefully we do what engineers call getting the right order of magnitude on the back of the envelope. But we, as we're seeing in the COVID-19 fighting, they throw out a big plan like for the whole country, but then they're using the data day by day and week by week to modify the plan, to learn from experience as fast as possible. So I say the smartest governments are using exactly this method. In Norway, we happen to be winning, is the message right now, with the methods that have been put in there, but the scientists are really driving it. We don't have a Trump at the head of the government doing strange things. At each step, you're getting more and more facts about what things really cost of the designs that you've decided to stick with, because they're okay cost-wise and they do the job. Here's part of the diagram we looked at earlier, where we're calculating the estimate to complete the system and giving early warning, like if we don't do something now, we'll run over the deadline or we'll run over the budget. So we'd better do something now. This is more or less like saying 2 million people will die in the US if we don't do certain things now, and then we can keep it down to 100,000. Something pretty much the same thing going on. So here is area 3 of 5, and we can call it contracting for results. And what it means is using all these methods we're just talking about now, but instead of having, as IBM Federal Systems Division, they had one overall contract and then they were on their own to manage that. So what we do is we have a framework contract, which does all the legal bits. But the contract really says we're not going to give an estimate for what the whole thing will cost or when the whole thing will be done. We're going to look at a release, as they call it here, and we're going to make a statement of work. And we're going to actually say, look, all we want to do is raise the availability of the system from 95% to 99%. That's all we want to do on one sprint here. In other words, improve a value or quality called availability by 4 points. And if we do so, we will pay you 1 million quid. Okay, and you can make an estimate how long time it will take you, and you can make an estimate of how much it will cost. But we will pay you. We will accept it. If you tell us it's going to take us 50 years to do it, we won't even start. But if you can do it within a reasonable time, like this month, we will start. And if you actually achieve the 99% availability, we will pay you 1 million quid, no matter how you did it. For example, even if you wrote no code and just reused code from something you had before, we don't care as long as we get our value results. So this is output or being output oriented or results oriented, not code writing oriented. So the deployment will measure have we reached 99% availability. If that's successful, we continue with that same contractual framework, and we say, okay, now we want to raise the reliability of the system from 99% to 99.99%. That's all we want to do, and we're thinking of doing that within a quarter of a year, and we'll pay you 2 million quid if you do it. Do you accept the mission impossible? And if we get a team that says they're going to do that, we could even have theoretically, very theoretically, parallel teams, and we pay the first one that achieves it and don't pay the other ones or something like that, or pay them a loser's prize. Anyway, so if within, and maybe even going through some internal iterations or sprints, the statement of work 99.99% availability is achieved, when we deploy it, that's considered successful. We pay them their several million pounds, and we keep on going through this. And we keep on doing this until the goal levels of all of the values are delivered, and then we have a definition of done. So we can also call this a no cure, no pay model. There are interesting variations on this, like you pay them half of what they'd like, but the other half is a bonus and things like that. So they've got some funding to carry things on. But I like the absolutely no pay if you haven't cured the problem. There are other variations of this. Let's say you move from 99 to 99.90, and you maybe got a fraction of the pay, but full payment when you get to 99.99%. So this is outcome-focused process, and the outcome is the value and value levels you want, and you reward people and motivate people by paying only when that's achieved, no matter how much code they've written. Okay. Here are some reasons why this deals with complexity. For example, you don't have to understand all 50 steps and how they accumulate and what they would cost and whether the supplier even knows what they're doing. You don't have to understand them up front for large complex projects. You have a rough overview, you hope for the best, but you prove yourself by improving the current state of play step by step, and prioritizing the most important things to be delivered first, and motivating the hell out of your sub-suppliers so they really do deliver. And the subcontractor doesn't have to worry about this either. Let's just say, for the sake of argument, that one subcontractor can do the first 10 steps successfully, but they are incompetent to do the 11th step. Maybe you have another more competent subcontractor step in and prove that they can take step 11 to 20. Things like that can be, but you're not locked into one subcontractor where they've gone beyond their level of incompetence. This method, you can also focus on quick wins and low risk or sure things, and until you reach a level of incompetence regarding your complexity. And if you do fail, or the supplier fails, you've only lost, say, approximately 2% if those are your step sizes, and you can continue the project by finding simpler, more risk-free designs, just like IBM Federal Systems Division did it. So there are lots of good reasons for doing this, but it's still a very unusual form of contracting, but it's not that far off from what's going on in the COVID-19 fighting. If you look at how governments are rewarding suppliers for actually delivering things, you know, like respirators next week in practice or something like that from Dyson or whoever it is. Here's another chart just showing that this flexible contract model, as it's also called, delivers on a number of agile points. Here's a website which gives you some framework contracts for the United Kingdom and the US, by the way, if anybody there is listening. And were developed by Susan Atkinson, who's a lawyer, and Gabriella Benefield, who's a Scrum teacher, by the way. And they used my methods as a framework for doing it. Here's a summary of what a flexible contract is. I think I've handled that reasonably well. We'll just let that be. Here's some of what you find on that website, like a template for specifying outcomes for your sub-suppliers. Here's a more detailed template where the exact level that we're going to pay money for. Here's how much money we're going to pay and how are we going to measure it. And then here is a more realistic example of what I do in practice using the planning language. Language is specifying, for example, air. Here's air quality, for example, and here's a scale of measure, number of persons who reside in London boroughs dying from exposure over time to pollution per year in a certain area. And then here are tolerable levels for example, seniors and children, and Greater London, both for different carcinogens. And here is a goal level, a success level. So what we're doing, we're specifying, by the way, status is where we're starting from. Tolerable is anything less than that, we won't pay anything, but beyond tolerable, we might pay a percentage of what they've achieved, but full payment will be paid when the goal levels are reached. And we can have many different goals for different types of people and different types of London and different types of pollution and things like that. So that you're looking at a very realistic example of the planning language for a requirement, which can be used in a contract to specify exactly what we're going to pay money for. So flexible contracting, how does it deal with complexity? Well, number one, if you've reached your level of incompetence and nobody can figure out a way, or this one supplier can't figure out a way of dealing with the complexity, everything you try fails, you can at least stop the next 30 steps and don't waste 3 years and 3 billion quid just wasting your money, as so many large government projects seem to do in both UK and other countries. If complexity is unexpected, we can discover it early, even by choice. Like, this is very high risk step, and I want to do it early, because if it does turn out to be more complex than we fear, at least we know it and we can look for alternative designs early. We don't have to worry too much about the total cost of everything of an extremely complex system in advance, because we're going to do it step by step, and we're going to get our worst case is we stop moving forward and we don't waste money. And our best case is every step we've done successfully, we only pay for it what we thought we'd pay, no matter what the complexity was. For example, the complexity might have cost the sub-supplier 5 times more than we pay them. That's their problem, not ours. I've done contracts like that for decades with organizations like IBM. As I said, potentially complex increments can be piloted early and defeated or found to be okay. I think I already mentioned that above. that's enough of that. Okay, so area number 4, got a half an hour more, about 15 minutes to the next two subjects, is that we can deal with complexity by being lean. What does that mean? Well, let's emphasize two lean components: doing things early as opposed to at the last possible moment, and preventing problems from happening rather than discovering late in testing, for example, that they have happened after 5 years of project. Okay, I'm going to focus on two methods. One we call specification quality control, the other we call defect prevention process, and they basically help us by dealing with things early and preventing defects from happening. In other words, early and preventative. First, we're going to take a look at specification quality control, which my son Kai and I invented for Citigroup in London years ago, and was very successful there. Within 6 months, they reduced the bugs by a factor of 10, just to give you a bottom line on the initial experience with the use of the method. And this is from a presentation done by Intel, which 21,000 engineers for 20 years have been using both my language methods for requirement specification and my SQC method. And so this is actually, the slides are mainly a report by Intel on the use of my methods. But Intel says, well, they prevent things from happening and they're early, and lots of other good things happening. Specification quality control, if we define specification, it means anything we specify, and that includes code, but it includes requirements, and it includes contracts and bids and test planning and architecture and anything we write down. So it's a very universally general tool, but in practice, the very first thing you want to focus on is requirements, because one fault in a requirement can lead to 10 bugs, put it that way. It costs 10 times less to find faults in requirements before they become faults in, say, the code or the system, which is which means we're dealing with the bugs early. Now, specification quality control, unlike testing and software inspection, is not about finding and fixing faults. It's about measuring defect density. It's not about cleaning up. Okay, and we use the measures of defect density to motivate software engineers, could be requirements engineers, to do things according to the best practices, which they may have forgotten or never learned, so that things are done right the first time. You may have heard that, do it right the first time, early. And now, one of the consequences of the fact that we're measuring and not trying to find all the faults is that we can check only samples, and that means we can check a 1% sample or 2% sample if it's representative. And that means the cost of doing this is about 50 to 100 times less than conventional software inspections. Again, when we find defects, we're not going to say fix those defects. We're going to say fix everything, including everything outside the sample that we looked at. So we're really just trying to say, is it necessary to fix everything? Do people have bad practices? And go back and fix it. We're going to focus on major defects, i.e. things that cause bugs and architectural things and cost 10 times more to fix or 100 times more to fix later. And this is a rigorous but consciously simplified process. There, by the way, is a little map of the process. Now, another point that Intel makes is you can use this at early stages of, for example, writing requirements, and you can use it at intermediary stages of writing requirements. Is the process still working? In other words, measure, maybe a month later, 6 months later, 9 months later for code or test case, test planning or anything, and measure finally before release. Are these requirements or this code a high enough level of quality? So the fact that it's so cheap means and can be done really in an hour or two in many cases, even for a very large complex system, means that it is practical to do it early and continuously and often and finally. So it's not like, it's very much like test-driven development in many ways. It's sort of integrated and done all the times. Here's another map from Intel where they say, look, we've figured out that there, for requirements, there's an acceptable quality level of defects per page, and we have to be within that range where it doesn't pay off to release the requirements at all. It pays off to fix them. There's a level which is so bad and so high, like 100 defects per page, that you've got to be kidding. It's a really bad idea to release the requirements to, say, a test planner or chief architect, because you're just going to cause more late-stage complexity and problems, and people won't be able to deal with it. This is like being overwhelmed by too many coronavirus patients. And this is when we've managed to flatten the curve and we can actually handle them, or maybe even prevent them from being patients at all. Here's some data which from a real example from Intel, where they were at these levels initially of defects, defect density. And these are not the scariest bad defect levels. People are pretty good. But at every one of these checkpoints, people were told, no, you're not good enough, 0.3. Sorry, this is revision 0.3, you're at 10 defects per page. And we've got to get, before we can release it, we've got to get down to 0.2 defects per page. So keep on trucking, keep on working. No exit from the process of, say, writing requirements until we get here. They report that the benefit of using this process is a productivity enhancement for the entire engineering team of 233%. So if you want to know how to double your engineering productivity, here is a real example from Intel using the methods I'm talking about. If you want a very much more detailed example, and if you look up, if you Google this title, you'll get the full paper. It's based on my language methods. It says very explicitly here. And this fellow, John Terzakis, is in Boston at Intel, and he is actually simultaneously teaching my methods, but he's researching how well they work over a several-year period and reporting about every 2 or 3 years in public. Great, I'm grateful for that, because then I can brag about it. And here's the example we just looked at. A team hands over for some chip project requirements, and it's 31-page requirements. They find 312 defects. Now, for example, if it said the requirement is to have high security, that's probably 2 defects. The word high is not clear enough, and the word security is not defined on a scale of measure. So we need to get rid of 312. And basically, that's a defect density of 10 per page. I believe their pages are 600 words here. And basically, no exit. This is not useful. You're not following our standards well enough. Don't you know that high security is not a good enough requirement? Try again. And they keep on trying, and they keep on going through a team learning curve or personal learning curve. This is a small team, probably about 4 people. And finally, on what they call revision 1, where they're going to release it, they have a 45-page requirements. They may have rewritten it completely compared to what they started with, for all I know, but they only have 10 defects, which is 0.2, which is 50 times better than the one they originally delivered. It's also a 98% reduction in defects, which is ultimately a 98% reduction in bugs and other nasty problems in chips, which is very serious business. So, by the way, this is about the same level that NASA requires for its Mars missions in quality. And they also learned this method from me at Jet Propulsion Labs, and Kelly and others, and Marilyn, what's her name, reported on it. You might not need such a high level as this, but you probably need a level of maximum defects like this, and you probably have 100 or 300 today, because you're not even measuring the defect density. So I suggest you learn about simple, cheap methods like this and get control of the complexity before it explodes into real code and real systems. Here's the review cycle, simple version of it, taking 60 to 120 minutes for each sample. How does specification quality control help with complexity? First, it pulls the same trick that we've talked about earlier. We do things in small increments, like we can do it on every 2% increment of what we're doing. And so if we discover that people don't know what they're doing, we don't let them do it 50 times more. We say, you clean up your act, and we won't let you get out of this 2% sprint or increment until you've got a higher quality standard. Most of Scrum and other Agile techniques are very open-ended in their framework and don't have such strong technologies for looking at the quality of each sprint. By applying this method to early stages like requirements and architecture, where a very large quantity of problems occur, and if you analyze any of the why projects fails, you'll find bad requirements and bad architecture are some of the major causes of why projects fail. If you apply it early, then you reduce this 50 to 100 times greater density and therefore complexity of problems that somebody has to deal with, for example, after code is written and during testing or in the field. This method also forces people to hunker down and really learn the best practices on the job, and it makes the learning process very focused on what have you not done now? What have you not learned now? Doesn't matter they went on a 3-week training course and have forgotten it, or they never attended the course. McDonnell Douglas, one of my clients, used this in their engineering for 3,000 engineers, and they said it's the most effective training course we've ever had. And as I said before, it doubles the engineering productivity, so you've got extra engineers to tackle the complexity. Here's a second technique, which was developed by IBM, and again, they were never very good at spreading it externally, but they used it internally very well and published it in IBM Systems Journal, but still, most people don't teach this, most people don't use it, which is a shame, because the defect prevention process can, within 1 year, prevent half of all the defects happening. Within 2 years, generally speaking, prevent 70%. And at IBM in Minnesota, for example, and at NASA, they were preventing over 95% or more of the problems. That means the problems never happened. They didn't have to be detected and corrected. So with this prevention area, it's like preventing people from catching the coronavirus. You don't have to detect it and say it isn't too dangerous. You don't have to wait until we test you in a car and say you can't drive into the country because you've got a coronavirus, and we don't have to worry about it being spread. So prevention is, an ounce of prevention is worth a pound of cure, as we all know. And we need to look more seriously at prevention techniques. So this is a prevention technique. Now, what is the technique all about? Well, you can read about it in these slides, for example, and it's published in our software inspection book from 1993, and it's published in the IBM Systems Journal, but this will give you the details. But the important thing about it that I'm going to tell you about is, here's an example from IBM labs in Minnesota, where in a 30-month period, Steve Kahn reported that they analyzed 2,162 reasons why the engineers were doing defective work, and they carried out 2,162 actions. That means real changes to the engineering process of several thousand engineers in IBM in Minnesota. And the interesting thing was that these actions were created by the engineers themselves, piloted by the engineers themselves, and if measured to be successful in reducing defects, spread to the entire organization. So here you have a form of grassroots analysis of what are we doing wrong and what are the simplest ways of changing our environment. This beats anything like, you know, using a new agile framework is a big idea. This is not a silver bullet. These are 2,162 silver bullets designed by the people who have to live with them. And that's very surprisingly powerful. The return on investment for this method, Raytheon also used it in a big study we have. They found it was 7-to-1 return on investment, but IBM found it was like 10-to-1 return on investment, depending on how you look at it. They managed to get the defect rates 50% lower, not bad, but they're also speeding things up. Now, how does the defect prevention process deal with complexity? Well, first, it gives a radical reduction, although it does take time to change an entire organization with thousands of smaller changes, but you do have to start that process working and give it time. The good news is you get a pretty damn good result within the year, and remarkably much better within 2 years. And then you might have to use 5 to 8 years to get up to, you know, 99% prevented. But it is a radical reduction in problems, and that's a radical reduction in future complexity. The other thing here is that it is the grassroots staff, the software engineers, that themselves identify problems and themselves suggest something outside consultants would not suggest, and outside suppliers of methods would not suggest, that the simplest process change they can live with. These are often things like just improving a slide in a training course that gets misunderstood by everybody, or improving the standards for coding or something like that. And they will not suggest things which they would view as unnecessarily complex for their work. So it's extremely practical that the change process is effectively delegated to the staff. And in the next 12 minutes, talk about area 5, and the area is called scale-free methods. Now, I'm sure you're all aware of the fact that the Agile people gradually began to discover that as they scaled up to, for example, large government projects, simple vanilla Scrum wasn't going to do the trick. And so things like less and safe and other methods came on the market, claiming to enable you to deal with enterprise size or very large methods. I took a look at these methods at one point and said, I am not impressed with them. I don't really like them at all. I think I actually have and long had much better methods. So I wrote a paper on it, which you have a reference to a copy of in a slide. And I sent the paper to my friend Eric Simmons. Now, this is the man that taught the 21,000 engineers from the year 2000 to the year 2016 how to do my methods. He literally was the key champion of spreading the methods. And he wrote back and he said, initially, Tom, your methods do not scale up. And I was really rather disappointed because I thought my methods scale up. They can deal with extremely large projects. I know that. I've seen it happen in practice on 1,000 person software projects at for example, Siemens years ago. And he said, no, your methods don't scale up. They are, and he invented a term I didn't think of called scale free, meaning they work at any scale. In other words, you don't have to have one method for small projects, one method for medium projects, and one method for humongous, complex and gigantic projects. One set of methods will work at any scale, and that happens to be my methods. How does he know? Because they've experienced that in practice at Intel for 2 decades. So proof of concept right there. Thank you very much. And he does specifically say that most Scrum practices are not scale-free, but of course we've all discovered that. In my paper, and here's a copy of the paper Beyond Scaling, which you can get right now from there. I wrote a list of the top 10 methods that I believe are scale-free. I then gave cross-references to sections of my value planning book, free copyright there, or other references in the paper here, Beyond Scaling, if you want more detail. But long story short, you'll discover that this talk has covered most of this anyway, so you have a pretty good idea of what I'm talking about. But if you want more pragmatic detail, you either come on one of our BCS courses when we start running them or broadcasting them, or you read the free books in the meantime. What else are you going to do in Corona's times except download my free books and become an expert on scale-free methods? Welcome. Here's a detail of one of them, method 7, which was to have this. This is the Gilb value planning cycle. Stakeholders, what are their values? Find the technical solutions, decompose them so you have small increments, develop and deliver, then measure, just like IBM Federal Systems Division was doing, the costs and the values. Learn from this, and then maybe find better solutions and continue this cycle until you deliver it good enough, and continue doing this until all the values are delivered. So now it turns out that cycle can be used at any scale of project, if you think about it. And certainly that's been proven at Intel and very many other Hewlett-Packard, Boeing, Ericsson, and other of our clients who've done our methods on a very large scale and reported publicly about it. One of my friends, Rolf Götz, sent me this lovely quote: "As to methods, there may be a million and then some, but principles are few. The man who grasps principles can successfully select his own methods." And I'm pretty much a fanatic on understanding principles, which is why I wrote a whole book about it with 144 principles called Principles of Software Engineering Management. And all my books and papers have one principle after the other, because they give a lot of leverage for understanding the multitude of methods out there. So Harrington Emerson, turns out, is the one who did that quotation. So just for fun, I wrote down the key principles with suitable references to either one of these if you want more detail, which in a sense this is worth studying, because these principles give you more leverage in understanding whether less is a good method or Scrum is a good method, or whatever you're looking at. But you'll also discover that I've been talking about most of these principles in this talk. So it's just the detail and the pragmatics of it that you'd be interested in going into more detail. And we have held courses for about 7 years at British Computer Society on these ideas. So some of you have been on those courses, and we were planning to hold some this week, and we might even produce those courses online. In the meantime, you're very welcome to read about it in your home quarantine for free. Okay. Here is one set of the methods, my own project management methods, and free references to do these things. But we're talking about how do you delegate the design to the software engineers and maybe take away a lot of the power of an architect or designer. No time for that, but whole books on the subject right there. So how does scale-free deal with complexity? If you get some rapid and unexpected scale-up, suddenly, hey, forget your normal virus problems. We've got COVID to deal with on an international basis in all countries simultaneously. That's a rapid and unexpected scaling up. The methods you're using, you can continue using the same methods, even with this 10,000 to 1 scale up, and they'll not break the system. You don't have to sit down and learn whole new development methods. You don't need to use completely different methods just because you had to scale up rapidly and discover after 2 or 3 years of development that it doesn't work and you've used the wrong methods for scaling up. If projects that would have failed due to unexpected complexity that either one sub-supplier cannot deal with, or no sub-suppliers can deal with, this will have been discovered at certain intervals by measurement. This is costing too much, it doesn't work, and we will reduce the projects will have succeeded up to that point, increment by increment, and they'll only fail at a certain 2% point. So your maximum loss is very much constrained in using the methods. So here's just a little note on scale free and a free copy of the competitive engineering book, which gives the language methods standards. And now I ended the talk 4 minutes before I should have ended the talk, which is probably a very good thing. As I may have mentioned at the very beginning of the talk, there are slides after this which go into some detail about the wicked problem assertions and why I think they are not true. So here's an example of the first one. And if you want that detail and want to study it, skip ahead and disagree or agree with me as you like. In the meantime, here are some nice freebies for thinking about the problems. And we're videoing this, and maybe we can probably share the video with people. And as soon as we can, I hope we get to run our courses again, either by video link or live when I can get to London and do it in person, as I had the pleasure of doing with BCS for several years now. And so end of talk. I don't know if we're going to do questions and answers by chat, but I turn over to Imo now.
Tom, thank you very much indeed. Yeah, we've got a question here from Thierry Ackermann, who's the speaker at a meeting I went to recently. He's asking you to return back to the contracting for results section of your talk. And he's wondering how you would apply that method to a large scale multi-year infrastructure project such as HS2, which of course isn't a software.
HS2. Okay, now as I've asserted, good thing I got the coughing spell after the end here, and I hope it's not coronavirus showing up with my cough. Let me drink a water here. I just unaccustomed use of my vocal cords, I think. Long story short, I made a suggestion that the methods in the competitive engineering book, they are systems engineering methods. They are, most of my work has been in IT, but I've done a lot of work outside of IT, such as aircraft corporations like Boeing. And the methods I'm suggesting work on any class of system. And we've, so I would suggest that HS2 could use these methods to plan the whole project and subsets of the project. In other words, I believe it scales up to HS2 level. I don't see any reason why we couldn't use, for example, this method for defining some of the quality variables of the HS2 system, both at the overall highest level okay. Now, I have personally only done projects at the level of a few thousand engineers. But we're beginning to approach HS2 levels, but they probably have 10,000 or 20,000 engineers over a 7-year period. So I have actually proven this at very large scale projects, not just in software engineering, but in systems engineering. So the short answer is the claims I'm making, I would assert, are valid for HS2. And I'd appreciate if somebody working on HS2 would like to discuss this with me, and they can certainly access the free literature and start thinking about it and come back to me if they believe that this method does not scale up to that level. I'd like to take the opportunity to prove them wrong in a friendly way for free.
I think the issue here is that something like a very large infrastructure project cannot really deliver value until it is substantially completed and open to the public.
Yeah, I've heard that claim for about 40 years, and every time we look at it, it turns out to be not true. Now, that is, people say that, you know, there's only something called the completion of the project, and that's the only thing that delivers value. And there's no time to go into it now, but I can hold a separate lecture on it. how do you deliver partial value at early stages in enormous projects? Okay, and now I've given a hint at it. For example, the whole IBM Federal Systems division in the real projects they were talking about were in fact delivering value on board ships and spacecraft step by step. They were enhancing the qualities of the systems long before the final increment was delivered. So the theory that you can do that is proven by the Federal Systems Division and my own experience. So I understand why people claim that you can't do that, but it turns out they do not know how to decompose systems. There is a chapter in the value planning book, which I've offered for free here, called Decomposition, of about 60 pages. If somebody'd like to study that, they'll get an insight into how we decompose systems so that we can deliver value much earlier than when the final HS2 connection is made.
Thanks very much. There's another question about HS2 here, which I'm not sure you want to get into because it's really asking a political question. Our delegate says the purpose of HS2.
Anything. Got nothing else to do except have dinner this evening.
Okay, I'll tell you what. Let's ask Alan to actually ask that question himself. I'm just going to unmute him. Alan, ask your question.
Yeah, it was slightly tongue-in-cheek in that HS2 does, of course, have kind of well-developed construction engineering methods. But my question was really, are people thinking of the right stakeholders, as these mega projects are really designed to deliver as much money to the contractors as they can get away with?
There's
but that's, that's part of your flexible contracting model, perhaps.
Sure. There's a stakeholder which is seeking to get as much money as they can, and there are politicians maybe trying to allocate money to their constituencies, or whoever's bribed them, or whatever corruption they're into this year. Yeah, true. There's all that's going on at the same time. So we recognize, in other words, HS2 is definitely wicked problem or highly complex problem.
Indeed.
But I am suggesting that the methods I'm talking about can better be handled. By the way, this table I'm showing you here, one of my 25-year students, a man called Chris Dale, has actually used this for planning Brexit, this table, and said it was the best thing for handling the complexity of understanding Brexit and presenting it to a ministry that he was working for. Okay. So that's a pretty large political problem, and yet this tool has actually been used there, and we actually have copies of it. Okay, which we presented for the first time on a British Computer Society course, actually, where Chris was present.
Thank you.
A pleasure. Thanks for attending. And do take contact with me if you want to, by email. If anybody wants to go deeper and pose me interesting questions, I'm very happy to take them by email, tom@gilb.com. I've got plenty of time during the coronavirus to answer your questions. But I'll warn you, maybe you should read one of the books first, or at least scan it, because I shouldn't have to read the book back to you. But if you don't do that, I will point you to sections in the free books, which in fact probably answer your questions.
At this point, I can point out that we've posted a PDF of your slides on the BCS SPA website. If you go to the regular London meeting program page and this talk, you'll find a link to it. Okay, and of course, in the slides, you'll find links to further resources.
Sorry, if that's right, I have tweeted today the location of the slides on my website. So if you Twitter Tom Gilb or LinkedIn today, you'll find the website mentioned.
Yeah, I was constrained by the 5 megabytes limit of uploads on the BCS SPA website.
Right. This is a 22 megabyte file.
Right. Which is why I made a PDF of it. Okay, we've got a question from Olivia. Oops, just a minute. There we go. Olivia, would you like to ask a question?
Hi, can you hear me?
I can hear you.
Tom, I attended one of your classes, or several in fact, when you were at the BCS. I think it was in
I think I
2018.
recognize your voice.
Hi. And, you know, and I came back, and every time I hear you, it's a fantastic refresher. And you really do go to those basic, I would say, engineering principles. And it's those principles that are, I think, not taught so easily, and they do take a while to comprehend on one level. But it's those basic things that are always worth hearing again. And you were excellent tonight. You were absolutely fabulous.
Thank you.
I look forward to when you do come back, because I remember, for example, the example you gave in the DoD about a commander.
Yep.
The one, I think, what is it, the 1 to 10? I forgot the steps. Maybe you can do that in the synopsis, because that was a fantastic example. Because
Yeah.
wherever one is in whatever, you know, so-called high-level system, and we talked about Brexit and big companies, but it applies to just very small projects as well.
Right.
Wherever
Well,
one is, this works.
yeah, I actually had a slide on that Department of Defense PERSINSCOM system, which shows a very large, government military system where we use these methods successfully. But I cut out the slide to fit into the time there. But it is a very
I
fun
appreciate that.
study
Yeah.
of doing this for extremely large systems and complex systems.
Yeah.
There's plenty of the books. The books contain typically about 100 case studies of named systems for named clients. So there's plenty of practical experience validating that these methods work for very large and very small systems.
Yeah. So I was more of a comment that I had. Look forward to your when you're next in London, whenever that happens. Yeah.
Me too. Can't wait to get back to London.
Yeah.
Right now, if I traveled over, I'd be 14 days in quarantine, and any attempt to get back, if there was a flight, I'd be 14 days in quarantine in Norway. So
Yeah.
tough to travel, but nice we can do this electronically. So
Yeah.
maybe we're going to hold some classes electronically. If we'll watch this space at the SPA and maybe the quality group for announcements.
Yeah. Thank you.
Thank you.
Well, if there are no further questions, I'd like to thank Tom in the very usual way we do that. Let's unmute everybody and give them a round of applause. Hang on a second, let me see how you do that. There's a way of unmuting everybody. Can't find it. Sorry, there is a way of doing it. Is anybody online who can tell me how to do this? Here we go. Let's give Tom a really great round of applause. Thank you very much indeed.
Thank you all.
Okay, thank you. Thanks for listening. The recording of this session is going to be available online sometime. I have to get the recording from the BCS, and you've got the references to the slides and to the many downloads that are available from Tom's website. Thank you for those. Yes. Super. Thank you very much, Tom. I'm afraid, Tom, I can't hear you. You seem to have muted yourself. Okay, everybody. Thank you and good night. And join us next month. Bye-bye.